Well, hello, welcome again to our journey into algebra and number theory, and this is the second video in our section on applications to number theory. So in this little section we're going to have a look at arithmetic functions and two particular arithmetic functions. So unique factorization that we talked about in an earlier video in the integers makes it possible to talk meaningfully about the number of positive divisors of a given integer and the sum of these divisors. So I'm going to define tor of n. This is a Greek tor. It's one of the letters of the Greek alphabet, tor of n, to be the number of positive divisors of an integer n, and sigma of n, this is a little Greek sigma and little s, to represent the sum of the divisors, of the positive divisors of n. So for example, tor of 12 is equal to 6 because the factors of 12 are 1, 2, 3, 4 and 6 and 12 itself, and there are of course 6 of those, and the sigma of 12 is the sum of the factors, so if we add all these numbers up we get 28, and so sigma of 12 is 28. Now, if we've got a prime, then it's pretty obvious that prime's only got two factors, one in itself, so tor of a prime is 2, and this happens if and only if, in fact, p is a prime. And tor of p to the alpha, well, if p is a prime, then alpha's a positive integers, then the only factors of p to the alpha are 1p, p squared, all the way up to p to the alpha. And so there are alpha plus 1 of these factors. Now we'd like a simple formula for tor of n using the canonical factorization of n. And that's fairly easy to get, because if you take the canonical factorization, so these are all distinct primes, canonical factorization of n, then tor of n is just the following. You add 1 to each of these indices up here, and you multiply them all together. And the shorthand way of writing that is to write the product 1 plus alpha I, where I ranges through from 1 up to r. And that gives the formula for tor of n. Now why is this true? Well, any positive, if I've got n in this form, any positive factor of n is going to have to be p1 up to pr, each to certain powers. Now these powers might be 0, so there might not be, the factor might not contain p1, in which case beta 1 would be 0. But the betas cannot be bigger than the alphas here, the corresponding alphas. So beta I has to go between 0 and alpha I inclusive for these powers to give me the factors of n. So I've got alpha I plus 1 choices for each of the betas, and then you're simply going to, so you've got alpha I plus 1, so you've got alpha I plus 1 choices for this one, alpha 2 plus 1 choices for beta 2, and so on. So you multiply them all together and you get this formula we had up here. And it corresponds to a unique factor of n and conversely, and so the result follows. So to work out, for example, tor of 72, we don't list all the factors of 72, we just prime factorize it, which is 2 cubed times 3 squared, and we add 1 to the 3, we add 1 to the 2, we get 4 3s, 12, and there's the number. So there are 12 positive factors of 72, including 1 and 72 itself. If we take the number 40,500, again, you wouldn't want to sit and write all the factors of this out and count them. Again, you use prime factorization. It's 5 cubed be 2 squared be 3 to the 4th, and so we just increase each of these numbers by 1, multiply them together, and we get 60. So this number's got 60 positive factors. Now, just out of interest, I've made up a little table of tor of n from the numbers in it from 1 up to 24, and as you go along, there's no obvious patterns. Well, there are some patterns here, they're not quite so obvious, but certainly when we get to primes, every time we hit a prime the tor of n bumps down to 2, but it can get bigger than that, of course, and get quite large, and then go back to being small again. So from the table, these numbers, tor of n, seem to behave fairly erratically, But if n is large, it can be shown that torr of n is roughly a log of n. This is log to the base e, in the sense that if I take the average of the sums, so this little bit here is the partial averages, so that means I add up to a certain point, and then I divide by n. And we take the partial averages, and if you then divide that by log of n, the number you get gets closer and closer to 1, and in the limit equals 1. Now that is not an easy result to prove. If you're interested in that, you can have a look at my videos on analytic number theory, which is a little bit heavier, and this result is proven there. A more obvious result that you can spot from the table is to ask, well, when is torr of n odd? So you look along, well, that's 4, that's odd there. There's 9, that's odd. There's 16, torr of 16 is odd. And that's it in the table there. And you might guess that torr of n is odd if and only if n is a square. And I'll leave you to have a go at proving that one yourself. Well, that's so much for torr of n. Let's have a look at sigma of n. So a function, well, before we get to sigma of n, I wanted to mention this idea of multiplicative functions. So a function f defined on the integers is said to be multiplicative if we're given integers n1, n2 that have no common factor except 1, so they're relatively prime, then when you multiply the numbers together and then apply this function f, you get the same answer as if you apply f to each of the n1s and the n2s separately and multiply them. Now it turns out lots and lots and lots of interesting arithmetic functions turn out to be multiplicative, and so it's a useful term. Torr of n in particular is multiplicative. You can see that without too much work. Now what about the sigma of n? So sigma of n we're going to define to be the sum of the divisors of n. As we saw before, sigma of 12 is 28. So we add up 1 plus 2 plus 3 plus 4 plus 6 plus 12, you get 28. And again, we start off by looking what does sigma do to prime numbers? Well, if it's prime, it's only got two factors, 1 and p, so sigma of p is 1 plus p. And that turns out to be true if and only if p is prime. Well, we look at sigma of 2 to the k, because that's the easy one to work out. So what are the factors? Well, there's 1, 2 goes into that, 4 goes into that, and so on up to 2 to the k. And this is a geometric series with common ratio 2, and the first term is 1, and there are k plus 1 terms. So using the formula, standard formula for the sum of a geometric series, this is 2 to the k plus 1 minus 1 divided by 2 minus 1, but 2 minus 1 is 1. So there's a nice little formula for sigma of 2 to the k. So we could work out, for example, sigma of 2 to the 5th, that's 32. And that's going to be 2 to the 6th minus 1, that'll be 63. Now we can take this a little bit further, because again, if p is a prime, then sigma of p to the alpha, well again, you can write down the terms. I'll get 1 plus p squared up to p to the alpha, and then that again is a geometric series, and with alpha plus 1 terms, common ratio p, and you can again use the formula for a geometric series and sum that. And that gives you your formula there in the case of a prime. We'd like a general formula in terms of the prime factorization of n, as we saw before, and the formula for sigma of n looks like this. It's exactly what we had here, except what you do is you take each of the primes in here, you calculate this quantity, and then you multiply them all together. Now, how do we see that? Well, I'm just leave you to have a think about the proof of that. I'm just going to give you a little hint here. What you do is you consider what is the effect of multiplying out each of these. We've got we've got R geometric series here. So you for each of the primes, you write down this series and you multiply them all out. And if you think about it, what you'll get is you'll get 1. You'll get P1, you'll get P2 from this 1 times the next bracket. You're going to get all possible numbers of the form P1 to the beta 1, P2 to the beta 2, and so on up to PR to the beta R, where the betas are less or equal to these alphas. And so when you expand this out, you're going to get the sum of all of the factors of n, which is what we want, and you can sum each of these geometric series in here, and each one will have that as its sum, and then you multiply them together. So that's the key idea there. I haven't written all the details out, but that's what it's doing. Just as examples here, if we've got, well, firstly corollary, sigma n therefore is multiplicative. That's not too hard to show now. And so again, we take the prime factorization of numbers. We want to know the sum of all the factors of 40,500. Well, that's just going to be sigma of 5 cubed, sigma of 2 squared, sigma of 3 to the 4th. So you can either use this formula up here, this geometric series formula. I generally, if these powers are not too big, I just do this. I just write down as 1 plus 5 squared plus 5 cubed. This one we've got a nice formula for. That's just 2 cubed minus 1. And this one is 1 plus 3 squared, 3 cubed, 3 to the 4th. And you can quickly work those out with your calculator or by hand. And you end up with 132,132. It's a rather cute answer actually. And that's the sum of all the positive factors of 40,500. Going backwards, which is an interesting exercise, if I give you what sigma n is, I'm going to give you sigma n is 60 in this case, and I want to find all the numbers, the sum of whose divisors is 60. So again, I'm going to look at the prime factorization of 60, and I'm going to try and write down all the values of n. Work here. Well, by the way, 59 is a prime, so 59 works. Sigma of 59 is 1 plus 59, which is 60. Now I'm going to start working out sigma of all the of these numbers here. So sigma of 2 is 3, sigma of 2 cubed is 15. If you go any further, sigma of 2 to the 4th is going to be 31, and that's not going to be a factor of 60. So we stop there. Now sigma of 3 is 4. If you look at sigma of 3 squared, well, that turns out not to be a factor of 60. So we only want ones that spit out numbers here that are factors of 60. Sigma of 5 is 6. Sigma of 5 squared is not a factor of 60. Sigma of 11, so sigma of 6 doesn't work. Oh, we're only looking at primes here, by the way. So sigma of 7 is 8, but 8 doesn't go into 60. Sigma of the next prime is 11. Sigma of 11 is 12. 12 does go into 60. Sigma of 13 doesn't work. 17 doesn't work. 19 does. You get 20. Sigma of 29 is 30. And if you go any further than this, then you won't get factors of 60. So that means I now look down through this list and I try and find which numbers here multiply to give you 50. So in particular, if I take 3 times 20 here, 3 times 20 is 60. So because sigma's multiplicative, that means 2 times 19. So sigma of 2 times 19 will give me 3 times 20. So 2 times 19 is a possible value of n, which is 38. If we look at 15, and can we see something that multiplies 15 to give me 60? Well, the 4 will do here. So 4 times 15 is 60. So I take 2 cubed times 3, which is 24. And nothing else multiplies to give you, there's nothing else here, no other combinations here that multiply to give you 60. So we only get 3 solutions, 38, 24, 59. Okay, so note here we need only look at those primes for which sigma p is a factor of 60. And that is the end of that little section, and we'll finish off this section next time with a look at some perfect numbers.